Hello, welcome to Basics of Finite Element Analysis. This is the 5th week of this particular course, and today is day 2 of this week. Yesterday we learned how to develop element level equations, and today we will extend that discussion in context of the overall assembly. So, what we will do today and possibly also tomorrow is figure out that how do we assemble all these different element level equations and bring them up to an assembly level. So, with that intent in mind, we will first define the domain. So, let us say, this entire discussion is going to happen in context of the bar under axial compression or tension problem. So, let us say this is my domain, and I am breaking this domain into 3 elements: element number 1, element number 2, element number 3. Okay. Now, so the global element, node numbers are node 1, node 2, node 3 and node 4. The local element numbers are 1, or node numbers are and 2 for the first element, then this is 1 and 2 for the second element, and this is 1 and 2 for the third element. Okay. Now, at this stage, when we have to, so what I will do is we will first write down the element level equations. So, for the first element, it is k 1 1, k 1 2, k 2 1, k 2 2, and we realize that these k matrices are symmetric, at least in context of our problem. U1, U2 is equal to F1 plus Q1, F2 plus Q2, and this is for element 1. So, everywhere I have the superscript 1. So, this is for element 1. For element 2, I have similar equations, but the superscript simply changes. So, these are the equations for element, the second element, and finally, I have the equations for the third element. Okay. So, our aim is, so these are 6 equations. Why do I have 6 equations? Because I have 3 elements and each element has 2 nodes. If it was a quadratic element, it would have 3 nodes, then we would have 9 equations. Okay. So, if there are 3 linear elements, then we get 6 equations. If there are 3 quadratic, then we get 9 equations, and so on and so forth. But ultimately, we want only 4 equations because there are 4 actual independent nodes. Okay. So, how do we do that? So, we do that by understanding 2 important principles. The first principle is that because in element 1 and in element 2 these nodes are physically connected, it means that the displacement of U2 is same as displacement of node 2 of first elements and node 1 of second element. Okay. So, this is based on, now suppose there was a crack here, then we could not have made this assumption. Okay. But because these are physically connected, it means that U2 for the first element equals U1 of the second element. If this was the case of temperature heat conduction problem, there U corresponds to temperature, then the same thing would hold. There temperature of node 2 for the first element would be same as temperature of node 1 of the second element. Okay. So, first thing is that we write down these equalities. So, these are known as continuity conditions. Continuity conditions for primary variable. We assume that throughout the domain of the problem, the primary variable, which in this case is U, is continuous. So, this is U2 for first element is equal to U1 of second element, and that is this global U, okay, global U. So, this is the first continuity condition, right. Likewise, I have also another continuity condition for at node 3. So, the equation for that is U2 of second element equals U1 of third element, and that equals global degree of freedom, which is U3. Okay. So, what I do is the first step, so this is my first step. So, what I do is that I make these modifications to my element level equations and I replace them by U2, and this is also U2, agreed. Similarly, because U22 and U13 are same, I replace this by U3. And then of course, I realize that U11 is same as U1 and U23 is same as U4, agreed. So, I replace this by U1 and I replace U23 by U4. So, what I have done is, so at this stage that I have replaced element degrees of freedom with global degrees of freedom. See, all these individual displacements at nodes, they are degrees of freedom. So, I have replaced element level degrees of freedom with global level global degrees of freedom. This is the first thing. The second thing I do is balance forces. Second thing is that I balance forces. What does that mean? Okay. Now, I had said that this is what? Distributed force, which is Q, and this distributed force which is Q, it appears in my element level equations as F, right. So, what I know is that the total force which is at, let us say, node 2 is partially due to forces on element 1 and also due to forces on element 2. It is not due to forces on element 3, right. So, total F at node 2, total F, and this F is only due to this distributed force. I am not talking about point loads at this time. Okay. So, total F at node 2 is equal to F due to element 1 and F due to element 2. This is again because node 2 is connected. If node 2 was not connected, if we had split, then this would not be the case, right? Then this would not be the case. If there was a crack, then this wouldn't be the case. So, what that means is that the overall force at node 2 F2 is equal to F 2 1 plus F 1 2. Okay. Similarly, I can say that F at node 3 is equal to its contribution from the second element, which is F22 plus contribution from the third element, which is F13. Agreed? So, this is the second thing which we note. The third thing which we note, okay, the third thing which we note is that, so this Q, these Q's are because of A times du over dx, right. So, from the first element, suppose this is element 1, and this is 3, third node. Then when I look at this element by itself, I have Q A for the first element and Q B for the first element, and for this node, for this element, this is element 1, this is element 2, this is Q A for the first element, and this is Q B for the for the second element, and this is Q B for the second element, right. I have written 2. Okay. And these forces Q's, if there is no external force, they only appear because I have cut it here, and in reality there is no partition here. So, these two, they have to cancel out and they have to become 0. So, the other condition for balancing forces is that at common nodes, sum of Q's is 0, okay. And that is what we also see through the definition, because what does this mean? A du over dx at x is equal to x2. So, this is what QB minus A du over dx at x is equal to x2, this is QA, and I am computing both the things there. So, this will be 0, okay. So, mathematically also this is there. So, what it means is that when I do my assembly level equations, I have to do two things. One is that I have to replace local degrees of freedom with global degrees of freedom, and also simultaneously ensure the continuity conditions for U. The second thing is that at interfaces I have to add up the forces, right. So, I have to add up F, and I also have to add up Q's. So, the way I add up these F and Q's is basically this is these two equations, I add them up, these two equations, right. When I add them up, what do I get? I get sum of F12 and F21 and Q12 and Q21, right. So, I add them up. Similarly, I add these equations. Okay. So first stage is I employ the continuity conditions and replace local degrees of freedom by global DOFs, and then second I add up forces at nodes which are common. Okay. So when I do that, what do I get? I get my first equation is still same. So this is my assembly level equation. And I know that when I add up Q's at the interfaces, their sums are 0. So this is gone. Similarly, Q3 is gone. So, and the definition of, so what is K1? So this is global, this is my global K matrix, right, global K matrix. So what is K11? It is equal to K111. What is K12? It is K121. Basically I am just, right, this is my equation 1. The sum of these two, this is sum of these two, second equation and third equation is my second equation, global assembly equation, right. So this gives my second equation, this gives my third equation, and this is my fourth equation, and this is my first equation. Okay. Any questions? So this is how I construct my global K matrix and global F and Q vectors.
Sir, if there is an external point load acting on, say, the
We will talk about that later. Yeah. So what I have explained, since he asked that, is that suppose there is a point load. So in this case we have assumed, not assumed, we know that Q's, QB at the interface, they add up and they become 0. They add up and then they become 0. But if there is an external point force, then what do we do? So we will discuss that question a little later, maybe in the next lecture or something like that. But this is how we construct the global K matrix if there are no point loads, if there is only distributed load applied on the system. If there is an end load, suppose there is an end load here, then the value of this Q4 will be that number. But suppose there is something in between, that is something we will discuss later. Okay. So this completes our discussion for the overall assembly process. We will now continue this discussion, and now we will start discussing about boundary conditions and how do we apply boundary conditions in the next class. Thanks.